So today we are going to talk about, we're going to kind of jump back to section 6.3 and talk about some properties of logarithms, how they work. This is actually kind of interesting because, well, for me, it's kind of interesting if you're a giant history / math dork like me, I guess, you can say it that way. A big part of the reason that people developed logarithms in the first place was to make arithmetic easier from the days when you had to do everything by hand. So what logarithms do, if you've ever seen or heard of a slide rule, this is how those work. But they let you turn multiplication into addition and division into subtraction and powers into multiplication, which you can then reduce down to addition sort of. In sort of a particular way, right? So it lets you turn like sort of more difficult arithmetic into easier arithmetic. And that all kind of relies on using some properties of exponents that we already know, like how you simplify powers on the same base when you're multiplying or dividing or raising a power to another power. So first, just as kind of a reminder again, because we can't say it too many times, an exponential statement like 5 squared equals 25 is equivalent to the log base 5 of 25 being 2, because 25 is 2 steps of multiplying by 5, or it's 2 copies of 5 multiplied together, right? That's what a logarithm is and how it works. It measures this number in terms of this base. So with that in mind, how would you rewrite or simplify this? The natural log, right, which means log base e of e to the 9th. How would you rewrite that as the equivalent exponential thing? What's the base here? E. Raised to the x equals e to the 9th. So what does x have to be then? You have 2 different powers at the same base and they're the same, right? Which is what it means to be equal. Then it must be that the powers were really the same after all, right? This is, use this in solving things. This is true because exponentials are all 1-to-1. Okay, so the thing to notice here is that the logarithm with base e and the exponential with base e effectively cancel out, right? They sort of undo each other. What we're left with is that this thing on the left-hand side is just 9. This is true because of the way they work, right? So rewriting it in exponential form, we see it. Or you can also think of it as being true because they're inverses of each other. And what you're doing when you take the log of an exponential is you're composing the 2 functions, right? You're plugging one into the other one. So if we think of this as function composition, it's do one function, the exponential, and then do its inverse, the logarithm. Well, when you do a function and its inverse one after the other, you end up back where you started, right? Which is the thing you plugged in the first place. So the same thing will be true, and this always looks a little bit weird, but if I did like e raised to the natural log of 9, that's a function and its inverse. It's the same 2 functions, just the other order, but the same thing would happen. Those would basically cancel each other out. Okay, that kind of makes sense. Okay, right on. So that's true. That's there. What we're going to be looking at is kind of both like how do we apply that and how do we extend that idea to kind of simplify stuff where it's not quite as I don't know, straightforward as that. Okay, so this is a review. This is some exponent properties. Say recall. How do you simplify 3 squared times 3 to the 5th? 3 to the 7th. Why 3 to the 7th?
because you're multiplying and exponential numbers are just multiplying.
Yeah. These powers, right? So it's the same base 3. So we don't really care about the 3 apart from the fact that they're both 3, right? 3 squared is just shorthand for what? 3 times 3, right? And 3 to the 5th is shorthand for 3 times 3 times 3 times 3 times 3, right? Okay, so you have 3 squared times 3 to the 5th. How many 3's do you have? 7. So how could I get there apart from just counting them on my fingers like this? What can you do with the powers that'll get you to the fact that that's 3 to the 7th, but the version where I don't have to, hold up my fingers to represent all? Add, right? 2 and 5 and 7. So just for the sake of doing it once, I'm going to write out that that's, nope, 3 times 3 times 3 times 3 times 3 times 3 times 3. 1, 2, 3, 4, 5, 6, 7, which is 3 to the 7th. But again, once I see how that works, a better, faster, more efficient way to get there than writing all of them out would be to just add the powers, right? Okay, so you multiply like bases, you add the exponents because again, it's just counting, right? Totaling them up. What about dividing them? Subtract, because it's 3 copies of 5 on top and have you hold up 2 fingers. All right. It's 3 on top and 5 on the bottom, right? So how many cancel? 3 of them. So you're like, yeah, sorry, I was holding up 2 fingers. Why? I don't know why I did this. This is stupid. Thank you. Because I didn't want to have to write out 7 copies of 5. That's why. 4, 5, 6, 7. So 1, 1, 1, 1. They cancel, right? And you're left with 1 over 5 to the 4th. But again, a better way to do that would have been 5 to the 3 minus 7, which is -4, which is the same thing as the reciprocal of 5 to the 4th. And I'm not simplifying, I'm not finding what 3 to the 7th is, because I don't care about what 3 to the 7th is. I don't care that it's 3, I just care that the bases are the same, right? The point is, this multiplication turns into addition in the exponent. This division here turns into subtraction in the exponent, right? That's the point that I'm really trying to make. This becomes that. This becomes that. So what about a power raised to a power? 2 to the 3rd to the 4th. Say again? Multiply, yeah. Multiply them because this power is shorthand for 4 copies of that multiplied together, right? And this power is shorthand for 3 copies. So you got 2 to the 3rd 4 times. Well, that's 3, 6, 9, 12. 2, right? Okay. So how does this work, or what does this mean about working with logarithms? First of all, I guess everybody okay with those? Yeah, okay. How does this work when we're dealing with logarithm? So take a minute, try to think through what each of these would be. Using what we just talked about. Okay, so first one, the log base 3 of 3 squared times 3 to the 5th. So we've got on the inside of the log, multiplying like bases. And then we're taking the log base 3 of a power of 3, right? So what do you end up with there? What does that whole thing simplify to? Say again. The log base 3 of 3 to the 7th, which is 7. You're taking the log base 3 of a power of 3, right? And what a log base 3 asks is how many copies of 3 or what power is this number? Oh, 7. Okay. Let me throw a step in the middle there. 3 to the 2 plus 5, right? That's how we got the 7. Just simplifying the stuff on the inside. Okay, but notice here that we're multiplying there. We're ending up here, right? So this whole thing is the same as just adding those two exponents. I'll come back to that in just a second. Log base 5 of 5 cubed over 5 to the 4th. Let's do it the same way. Let's just simplify the stuff inside. 5 to the 3 minus 7. So 5 to the negative 4th. And that would be negative 4. Because again, a function and its inverse, right? The base 5 log and the base 5 exponential, or what power of 5 is 5 to the minus 4? Well, minus 4. And then the last one, the log base 2 of 2 to the 12th is 12. Okay. Now again here, see 3 and 7. We, just like we did in the step before, we added here, we're subtracting then, and then we end up at minus 4. Excuse me. Now, these log properties that we get out of logarithms are all kind of related to this. This is an example of what it looks like when the bases all match. When the bases all match, things clean up really nicely, but it turns out that you can do the same thing in other places as well. There's kind of 3 things that we get. One is the product rule for simplifying multiplication. Product is what we call the thing that you get from multiplying, right? And just as an example, if you want to take the log of x times y, that's the same thing as the log of x plus the log of y. This is what we saw in that first one up above, the 3 squared times 3 to the 5th. Yes, 3 squared times 3 to the 5th is 3 to the 7th. Then you're taking the log of that, so you get 7. But you can also do it by doing the logs separately and then adding them together, right? The log base 3 of 3 squared is 2. Log base 3 of 3 to the 5th is 5. 2 of 5 is 7. It turns out that that works in other places as well. So if you're looking at a product, well, inside a logarithm, you can split that and turn it into addition, right? So you got to compute a log, but addition is much easier to perform than multiplication is, and it's also going to help us in solving and stuff like that, because this works either direction, right? These are equal, which means they're the same, which means I can either go this way and sort of use it to take a logarithm and expand it or break it apart, or I can use it this way to take the sum of some logs, addition, right, and combine them, sort of squish them into one logarithm that's, got multiplication inside, but maybe this is easier to work with for solving or something like that. Remember, we've been talking a lot about trying to, get the thing to a point where you've got a logarithm kind of all by itself, then you can rewrite it as an exponential. This is going to come up in solving because I might have, several log terms, but if I can combine them, then I can use this, rewriting idea to turn it into a thing that we can deal with. The same but opposite thing is true for a quotient. For simplifying division, this would be like the second thing that we looked at a minute ago. The log of x divided by y is the log of x minus the log of y. If you want to use the sort of analogy that logarithm is counting how long a thing takes, it's all sort of built up in terms of multiplication and stuff. So a product here, asking how long it takes to reach that product is, well, how long it takes to get to one, and then also how long it takes to get to the other. Division, you can do sort of a similar idea. It's, take away instead. And then the power rule. The log of x to the, I don't know, a. Some exponent is a times the log of x. And that one is for the usual reason of how power works, right? If this is, think of this like a whole number, like it's x squared. Well, x squared just means x times x. And if it's x times x, then it's the log of x plus the log of x. But I can just combine that into two of them and I'd write it as 2 times the log of x. This just says that that works no matter what the power is, whether you can think of it as a whole number of them or not. So all of these things work in both directions. So again, we can use it to either sort of, break things up, right? Take a like complicated log and turn it into a simpler thing, or combine them. So if you flip over to the back real quick and take a look, or look at the stuff at the bottom of the page there. To sort of practice this, we're going to work on either expanding, which is like taking a single, like look at number 2, maybe at the bottom of the page there. Take a single logarithm that, the stuff inside is sort of complicated maybe, and break that up into simpler pieces. That one's going to break up into 3 separate pieces. Or take separate pieces where you've got logs with the same base and combine them into one. We'll call that condensing. I'll probably say condense or combine just about every time I say it. We can use that for things like, we'll do it just for the sake of practicing it, but that comes up as being kind of a handy tool to have in solving stuff, because again, if our goal in solving is often going to be like isolate the thing if you can and then get rid of it. Well, if there's more than one log term in there, one way to isolate is to combine them, right? Squish them all into one so you can get it by itself. Okay, so let's take a look at these 3 examples, and then we'll spend some time just working those practice problems back. So our goal here, basically, if we're trying to expand a thing, is to sort of take it as far as we can get it, right? So what you're allowed to do is take on the inside of a log, break up multiplication or division or powers and simplify those. And then if you can evaluate a log further, like, say it's exactly 3, then you can do that. So the log
What's the base here? 10. LOG, no base written, means it's base 10. 2x, 2x means, well, how are those things actually like connected or combined? Multiplication. So the log of a product becomes the sum of separate logs, right? So how would you write that? The log of 2 times x would become the log of 2 plus the log of x. Yeah.
The base here is 10, so the log of 2 doesn't clean up to, it's not like 3 or something, right? So I'm going to leave that as it is. X is just x, it doesn't mean anything here. So I can't do anything else with that, but I can split this thing up into those 2 separate logs. Okay?
All right, so y'all tell me about the next one then. 5x divided by 4. So it's 5 times x divided by 4, right? So the log of 5 plus the log of x minus the log of 4. Good. And the bases just match all the way across, right? I didn't read the bases off. The base is 3 all the way across, though that just stays the same, right? There's not really any reason to ever change that. Here, all we're trying to do is make sure that we've got a feel for how these properties let us break things up. So this multiplication turns into addition. This division turns into subtraction. Then I would just check the log base 3 of 5. That's not going to clean up, right? Like that's not, that one's not going to be pretty. Log base 3 of 4, same thing there. So just leave those as they are. Okay. All right. How about the last one? Log base 2 of 1/2 times x cubed. So first, I'm going to break that multiplication up because the multiplication is the thing that connects the pieces there, right? The cubed is only on part of it. So the 1/2 is the first thing to go. Multiplication is going to turn into addition. So the log, I said a wrong thing a minute ago. We're going to break the multiplication up first. Sorry. So that would be the log base 2 of 1/2 plus the log base 2 of x cubed.
And then within those pieces, I'm going to look for more stuff to do, right?
So basically now I'm going to just kind of zoom in and think about these one at a time and decide if there's anything else we can do with them.
The log base 2 of 1/2, is that one that we can evaluate? That's going to come out nicely. Is there a good way to think of 1/2 as the power of 2?
It's the reciprocal, right, of 1/2. So, if you wanted, we could go on a whole sort of side thing here. That's 2 to the minus 1. So what's the log base 2 of 2 to the minus 1? So that's -1.
Can we do anything else with the log base 2 of x cubed?
Three things that we can, sort of break up or simplify. Products and quotients and powers, because those are all really just sort of different faces of multiplication.
Products and quotients and powers.
Well, x cubed is, it's x cubed or it's x times x times x, right? So that's the same thing as 3 copies of the log base 2 of x. Now, I don't know what x is. X doesn't mean anything here. It's just a stand-in. It's just a parameter that it is. But I can take that 3 and sort of bring it down. That's that. Now that would be as far as I can go, right? Because -1 obviously is just a number. 3 times the log base 2 of x. I don't know what x is.
So that's as far as I can take that thing, but hopefully you kind of get a sense of, how this, might be useful in working something out. Right now, I've got a simpler thing to deal with here. Maybe that makes life a little easier. Or again, we can go the other direction. Maybe life's gonna be easier if I combine stuff so that I've just got one log term that I have to deal with.
Do we have any questions about anything so far? Okay, well, we got about 15 minutes left, so let's just spend some time with some of these. So instructions here, you're either trying to expand or condense. If you want to expand, you're trying to turn it into a bunch of simpler logs. That's like what we just did, right? We're taking a single thing and splitting it into several simpler pieces. Condensing would be like working the other way. So going from something like this and turning it into that. If you're adding, that means that inside the log, when you combine them, you're combining into a single logarithm, and inside there, you're going to be multiplying those things. So 5 times x. And then if you're subtracting, it means you're going to divide by it inside the log. So divided by 4, this becomes the log base 3 of 5x over 4. Excuse me. All right, so you'll take 10 minutes or something and work some of those, talk about it with people around you, and we'll talk about a couple of them in a minute.
X squared. So. It's just 2 out. And then log base 3 of 9. So this is just 2. Just make sure you
Yeah, and then typically what we would do with that, because that's sort of like compound fraction thing is sort of weird. Right, you get that? Yeah, right. So typically what you do with that is you're dividing by n squared, dividing by a, so. Right like that. Like any, whatever you're dividing by, ends up the bottom fraction. Basically, just because this compound fraction, like fraction within a fraction. Right, yeah, so those things are equivalent to. Yeah. Good so far? Good so far? Now just X and Y are just, no need to place on whatever, so like, those are fine. This you can. Yeah. You can just fine. That's when it comes out. Yeah. Yeah. Yeah, good. Which is. Is that right? Yeah, so, the coefficient of growth, that's like counting how many we have, basically. So it's kind of doing a different thing. Yeah. And stuff, so it's just like. There's not really worry about. Here with the more stuff goes on, right? Start with the biggest thing. It's the visual. That's the thing. Start. And then sort of zoom in and look at it small. Okay. Yep. Okay, let's talk about just a couple of these real quick. I mean, as always, solutions are on Blackboard. I don't want to spoil all the fun. So, you make sure that you spend some time with it. But let's talk about a couple of them, just to make sure we're on the same page. What can we do here?
Where should we start? So there's multiplication right there. X to the 5th times y cubed. There's division here. dividing by 9. So this is going to turn into the log base 3 of x to the 5th plus the log base 3 of y cubed minus the log base 3 of 9. All right, the product turns into a sum or addition, right? So we're adding here, division turns into a difference or subtraction. So subtracting there. And then just kind of look at each piece one at a time and see what else you can do, right? So the log base 3 of x to the 5th, I'm not going to worry about anything else for the moment. I'm just going to look at that. What else can we do there? There's a power, right? And that power can come down. So this is 5 times the log base 3 of x, or 5 copies of the log of x, right? Because x to the 5th is 5 copies of x. So inside a logarithm, you can break that into 5 copies of the log. Excuse me. Same thing here. And then the last piece is a number. So the check that I would want to do there is that log one that would work out nicely? Is that one that comes out clean? The log base 3 of 9 is 2. I don't know what x is. I don't know what y is. I can't do anything else with this, right? That would be this thing sort of fully expanded, fully simplified. Okay. Questions? Okay, cool. About something like 9. Now we're going the other way, right? We're combining or condensing. Lots of just dummy variables in there, right? B and K and M and A, like nothing means anything, right? So we're just focused on the properties of how we combine these things using logarithms. So what I would start with is that because you got this 2 outside a big set of brackets, distribute that. So that's 2 times the log of K minus 2 times the log of M minus the log of A. I'm going to write out a whole bunch of steps here just so that, we can follow along, but you'll probably get to the point where you can, shorten this a little bit. These come in as exponents. And then we're subtracting, and subtraction becomes division when you combine them, right? So I'm going to take these 3 things and mush them into one log now. And inside that one log, we should have, we should have K squared divided by M squared divided again by A, right? But that compound fraction thing is weird. When you're dividing by a thing and then dividing by another thing, it's equivalent to just write it as one division, where all the stuff you want to divide by is in the divisor, so it's in the bottom. So this is K squared divided by M squared and also divided by A. That. So kind of the shorthand version ends up being that things that were positive to begin with, right? Like log terms that were positive end up being in the numerator. Things that were negative to begin with end up being in the denominator. Okay, and then maybe one more real quick. How about 11? So split the division up. I'm going to do a slightly faster version of this. Split the division up. split the multiplication up. So that's the log of 5 plus the log of e squared. Right, that multiplication becomes this addition. What can we do with this piece? Log of x plus y squared. Well, there's a power inside it, right? Which can come down. So that's 2 times the log of x plus y. Okay, natural log of 5 is not pretty, so we're going to leave it as the natural log of 5. Natural log of e squared is, how many e's are in e squared? 2. Can you do anything to break the log of x plus y up further?
Two separate things for X and Y.
No. All right, everybody, eyes on me for a second. Can you do anything to break up the log of x plus y further? No. Can you distribute a log? No. Can you break logs up over addition or subtraction? No. The only things you can do are, because logs deal with multiplication, right? Logs are exponents. The only things you can do to break them up or simplify them are these 3 things. Logs play really nicely with multiplication and division and exponents because multiplication, division, and exponents are all really the same thing. Logs do not play nicely with addition and subtraction. Addition, subtraction inside a log, like we saw in this last one, you can't do anything with that. This stays like it is because, again, logs don't deal with addition in a nice way. They deal with multiplication in a nice way. So that you can just leave like it is. So this is as far as you can simplify this thing. So that'd be it. Okay? All right. So finish whatever else you need to finish there. And I'll see you all on Thursday. Have a good day.